Assalamu alaikum everyone, welcome to today's video where we will be starting off the chapter solution of linear equations, essentially a new lecture slide, lecture 3 actually in our case. So let's get started. In this slide, overall the discussion is about what is general representation for system of linear equations. To discuss whether solution exists or not, then we will get to know about two type of finding solutions, one by elimination and the other by iteration. And lastly we will learn about ill condition system, where we will try to recollect some of our old memories, where we will also talk a little about matrix inversion. And so starting off with the general representation, you see in the previous chapter we also studied a general representation, where we actually studied a general representation of a polynomial. So now it's not a polynomial, we are going to go for a general representation of system of linear equations. Okay, so usually this is a very well known equation actually. Ax plus by equals to c. If we recall correctly, ax plus by equals to c is actually a linear equation. No matter how you however you look at it, it's actually a linear equation. So what is actually a linear equation? To be honest, from this equation we can actually write something like y equals to mx plus c format. Okay, so if we can write it in y equals to mx plus c format, it is actually a straight line equation, that is a linear equation. A linear equation is basically dependent on the dimension that it is presented in. So usually when we write about linear equations, what we actually want to recollect ourselves with is that, you know, if we can draw two axes, and over here I don't know, probably something like this, a straight line over here. So this is actually a straight line, and the equation that actually presents this line is a linear equation. This can be this one, or just x plus by equals to c. These are all actually straight line equations, because, you know, from this one we can also write something like y equals to c by b, and over here we'll get minus a by bx, something like this. Okay, so this is actually y equals to mx plus c format from this equation to this one. So these are all actually straight line equation. Now the thing is, what is this word saying that relation with x is thus dimension? What is this relationship with x is and thus dimension? Well, actually over here what you can see is that there are two dimensions, right? This one is called the x1 and this one is called the y dimension. Okay, what about in case there were three dimensions like this one? In this case, what will happen? A straight line may go from here to here, and it actually might have three axes in xyz planes. So it's a straight line. What actually matters, it just matters that it's not a curvature. Okay, like this one is actually a straight line, but it stretches through three ways. So this equation was easily presented using ax plus by equals to c. What about this one? For this type of representation, what we need is actually a more dimension based approach, that we can actually say something like ax plus by plus cz equals to d. Now that's more like a straight line for a three-dimensional plane. So this is a three-dimensional plane straight line equation. This is a two-dimensional plane straight line equation. So this is what we meant when we said relation with x is thus dimension actually determines how the equation will look up to. As long as the x is dimension variable, not in multiplication, they are called a linear equation. So what does this mean? So over here you can see what is the x is variable. For example, this is x is an x is variable, y is x is variable, z is an x is variable, and over here we can see that none of them are in multiplication form. Now multiplication can be of different forms. I mean, you can say that x square is actually x into x, right? Sorry, we can say xy is actually x into y. So as long as axis or dimension variables are not in multiplication, it's a linear equation. For example, over here we can see x, y and z are not in multiplication at all, so this is a linear equation. But however, if we write, you know, something like x cube plus 3x square y, then you can see this one over here, we have 3x's, we have x twice and y once, so this is not a linear equation. So this one will not be a linear equation, this will be a non-linear equation. So that's about it over here. Now let's move on. So linear equations can occur in more variables. Just as shown in the previous slide, we saw that it was presented using 3 dimensions. It was presented in 3 dimensions. We already are very much used to the 2 dimension. There was 3 dimension, but in reality, if you remember your previous math experiences, you actually have done equation in higher dimensions, I mean a huge number of dimensions. So actually there can be, the equation can be presented in n dimension. Over here we are trying to show that you can express it in an n dimensional space, starting off with the x1. Over here the x subscripts are actually dimensions, a1, x1, a2, x2, a3, x3, and goes on till an xn, and we will have a variable b over here. So we can say, if we recall correctly, we can say that ax1 plus bx2 equals to c, right? X plus by equals to c. We also wrote something like ax1 plus bx2 plus cx3 equals to oh, okay, this one should be b, right? Sorry about that, I have to change a little bit to make it concurrent with what we studied earlier. So what we're gonna say is a1 x1 plus a2 x2 equals to b. This is similar to ax plus by equals to c. Okay, ax plus by equals to c. And for the third degree equation, we can write a1 x1 plus a2 x2 plus a3 x3 equals to b once again. Now we can say ax plus by plus cz equals to d. If you want, you can pause the video and go back a little bit and see that equation and compare them. So what we're trying to say, that this is the general form of any linear equation. We can write it in this format. Over here, ai, where I is represented as 1 2 3 till n, are real numbers, and at least one is non-zero. This is very important to note, that at least one of them has to be non-zero. Why? Well, if none of them are non-zero, that is all of them are zero, our left hand side will become 0. So let's say that a2x, or let's look at this equation. If this one is 0, there should not be any problem, this term will vanish. Okay, this term will completely vanish, and this term will remain. So it will be a working equation. But if all of them become 0, okay, then this left hand side becomes totally 0. So at least one of them needs to be non-zero to make it a working equation. Okay, so now we are studying system of linear equations, not a single linear equation. So we are trying to make it a system of n linear equations. So what we have to do, we have to write n different linear equations all by themselves. System of n linear equations is represented over here. There we have a till n axis, and they're actually m equations, my bad, sorry, they're m equations. So this can be presented using this kind of representation. So this is actually a representation of total of m different equations, and all having the same structure as shown over here. Now what we've been trying to say, that all these values actually can be represented using this one. So how is that happening? Well, it's not that difficult to see. You can see that over here we have a11, a12, and it goes till a1n, and you can see the pattern is same over here, a11, a12, and it goes till a1n. Just below them is a21, then okay, it's just a21, a22, and this is the pattern. Actually, we just collected the values associated with the axis and converted them into the matrix, and over here in the right side we just added the constant parts. So we can say that this matrix actually represents this equation in a total. Well, there's actually a fun part of this in mathematics. If you know, that's good. If you don't know, if we write x equals to x1 x2 dot 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 xn, and if we write b as another vector of b1 b2 dot 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 bn, and we have over here our a, then actually you may give it a shot. You can see ax equals to b. It's an equation, you can go for it. Matrix multiplication is required over here between a and x, and you can see the results. It's quite interesting. If you may, it will be quite an interesting one. So let's move on. A system of n variables need at least n equations. Very important. A system of n variables need at least n equations. Why? Okay, suppose let's go back to the old day mathematics. You have suppose two equations, 2x plus 3y equals to, I don't know, okay, 8, and plus 4y equals to 11. Okay, you now over here we can say easily that this equation, to solve this system, okay, we did a lot of maths in our older classes. If we know that without having two equations, suppose if I don't have this equation, I will never be able to solve this math as a whole. But if there was three variables, I mean if this was minus 8z equals to 4, and this was minus 11 z equals to, I don't know, 6, then we know the two equations will not be enough as well. We will need another equation, and this is what I'm trying to say over here. A system of n variables need at least n equations. We cannot work with less equations. We need more equations, and actually more than n are better. Systematically, statistically, the more equations we have, the better it is. If we have less equations, it means no solution can be achieved in most cases. Okay, so this one is actually just an extra information. The system is called homogeneous when all constant b are 0. That's all the values in the right side are 0, then we call the system a homogeneous system. So this is just to let you know. So now let's discuss about the existence of a solution, whether or not a solution exists. This is the discussion we have next. So what is the existence of solution? Over here we are seeing four different graphs. If you look carefully, there are four different graphs, and if you watch the slides which has been shared earlier, all these graphs and lines drawn in are actually represented using equations. I don't know if it's pretty clear in this video or not, but if you go to the slide, they're written quite clearly. You can zoom in and watch it. So over here, first off, I'm going to work with the first graph over here. If you look carefully, there's a blue line and a red line. There are two different equations, and if I solve this equation, I can say that the solution point will be this one. Okay, because both the lines actually intersect this point very clearly. So this will be the solution point, the point where both the equations are satisfied. So this will be easily caught. Okay, what about this one? This is second equation, and we can easily see that they are actually looking quite parallel, and in systematic terms what we call it, that they will meet each other in infinity. They will meet each other in infinity, so they actually are not meeting over here, and to be honest we can call them parallel. So they will actually not intersect at all. They will never intersect at all. So this is another type of equation. So if I am given this equation, what you can say, that there is no solution existence. The existence is null. Over here there was an existence of a solution, but over here no existence. So that's one way to say it. And how about this one? Another interesting fella. Over here I have written two equations, but actually what I see is that these two equations lap with each other. So when they overlap, then there is actually a huge number of solutions in existence. Over here we saw that there's only one solution, over here we saw zero solution, and over here there are infinite solutions, infinite amount of solutions over here. And this is another way to say. And finally we have this one over here. So what's happening over here, you can see that these two equations, there are two equations and they actually collided over here, right? They actually collided over here, and um, once again they separate over here. We can see a straight difference over here, and we can anticipate that as it goes on, the gap will increase. As if you go back over here, the gap will increase once again. But over here there's a huge region where we can see they're very close. And when we started studying numerical methods, we actually always said about approximated solution, right? We never actually anticipate that we will get the correct solution always, but we always try to get approximated solution. So now think of that concept over here. This will bring a huge disaster. Why? Well, it will bring a huge disaster because over here I can say that when the solution is approaching, it will find that the deviation is high between these 2 points, right? So it will say, no, I don't have the answer. It will try to reach this one. But over here you can see, even at this point the deviation is so low, right? The deviation is so low. So I have a huge region. If I solve these equations by hand, I will find that the solution is only 1 point. But for a numerical method approach, the region of solution will be too high because it is taking approximate solutions. Hence this is a problem for numerical method, and this type of problem has a name that we have already studied earlier. We have said the name earlier, but now in a different context. It is called, the system is ill conditioned. So once again, if you look at the graph, if we say the first graph, it has a unique solution. If you remember the second graph where they were so parallel, it was system has no solution. Next one, if we say so, the system has solution but not unique, there are infinite number of solution. And finally the system is ill conditioned, which means that it's hard for a numerical method to guess correctly what will be the answer. Next step is solution by elimination, but let's keep it up for the next class. So let's keep it simple and close today's session. Thank you everyone. Hope to see you in next class.